Hello, welcome to my video on data structures. In this module, I will talk about a data structure called array. In C++, it is also known as vector. In this specific video, I will introduce the basis of array and talk about three simple operations supported by array. Imagine you're running an online business and wish to store the information of the items you sell in a computer. The information may contain the name of the item, the popularity of the item, the price of the item, the availability of the item, etc. We assume that the information is well structured. That is, for each single item, we have a field that is dedicated to store its name, a field dedicated to store its price, and so on and so forth. In this case, because we will use the same number of data fields to store the information of each item, we can expect that the space we need to store different items is the same. In this case, the easiest way to store these items is to put them one after another as continuous memory blocks. Consider the figure shown here as a snapshot of the memory space. The shaded blocks are occupied by other processes, and the empty blocks are the free ones. We store our data in the green blocks. In the first green block, we store information related to item 1. In the second green block, we store information for item 2. And up to the nth green block, we store information related to item n. We call such a data structure an array, or vector as in C++. Note that at this point, we do not care too much about the ordering of the items. We might simply order the items based on when we started to sell them. And we will talk about what should we do if we do want to store these items in specific order later in this module. Now, given that we have stored our data as an array, we may need to access and update the data in some cases. Here, we list the three simplest data access and management operations. First, we may want to retrieve the information of a given item. Second, we might want to add a new item into the array. And third, we may want to delete an existing item from the array. To implement these operations, the key we need to keep in mind is that the data elements are stored in continuous memory blocks in the array. Now, let's go over the high-level ideas for each of these three operations. First, let's look at the data access operation. Because we know that the data elements are stored in continuous blocks, we can easily calculate the address of the element we want to access. For example, if we know that our data is stored at continuous memory blocks beginning at address A0, the address of the ith item will be simply A0 plus I minus 1. In other words, if we know the index of the element, we can access it in constant time. This is one of the major advantages of the array data structure. And as we see, the constant time access is granted by the fact that the elements are being stored continuously. However, as we will see in the next two operations, the storage strategy will make the data insertion and deletion more challenging. Now, let's see what do we need to do if we want to add a new element into the existing array. Since we do not care about the order of the elements, we can simply add the new element to the end of the array. When the next memory block is available, the new element can be directly added, and it takes O1 time. However, it could be the case that the next memory block is not available. For example, in the figure, we can see that the next memory block is currently occupied by another process, and we cannot write any data to it. Meanwhile, because the data elements need to be stored in continuous memory blocks, we cannot simply write a new element to an arbitrary free memory block. To address this issue, what we can do is to find another place that has n+1 continuous free memory blocks available. Once we have found such a new place, we move all data from the current place to the new place. In the figure, the yellow blocks represent the old place where our data was originally stored, and the green blocks represent the new place the data is moved to. And finally, we add the new element. Of course, moving such a huge chunk of data is not free. In fact, it may take O(n) time in the worst-case scenario, where you move the data blocks one by one. Note that the overhead is also due to that the data elements are stored in continuous blocks. To tackle this issue, we can ask for more space when we need to move our data. For example, instead of asking for n+1 memory blocks when adding a new element, we can ask for n+3 memory blocks as shown in the figure. In this case, we know that the next two data insertions will not trigger the expensive data move. In practice, we often require twice as the current space when a data move is triggered. Finally, let's consider the data deletion operation. Again, in addition to deleting the element, we should also keep the data elements in continuous memory blocks after the deletion. As shown in the figure, imagine that if we need to delete item I from the array. After deleting the element, we have created a hole between items I-1 and I+1, which makes the data storage discontinuous. To eliminate the hole, we simply move all data blocks after the hole one block ahead. That is, item I+1 will be moved to the ith block, item I+2 will be moved to the I+1th block, and so on. After the move, we will again have the data stored continuously. Similar to the data insertion operation, moving large chunks of data could be expensive. In the worst-case scenario, the operation could take linear time, O(n). Unfortunately, there seems nothing we can do to make it faster for the array data structure. Let's summarize what we have learned in this video. We have learned the basis of the array data structure. The array data structure simply stores the data elements as continuous memory blocks. This storage strategy makes data access very easy, as we can compute the address of the data element given its index. However, this strategy also makes inserting or deleting data challenging. When inserting data, we need to ensure that we have sufficient space to hold new data. Otherwise, we will need to move the existing data to a new place, which is quite expensive. To mitigate the cost, we can reduce the frequency of data move by asking for more space than we actually need. When deleting, we need to get rid of the hole by moving all subsequent data one block ahead. That is, again, a very expensive operation. However, it seems that we cannot do anything better for data deletion. We will provide a solution when we discuss a new data structure called linked list in the next module. Alright, that's all for this video. Thank you for watching and look forward to seeing you in the next one.